Alrighty then. So section 5, or 2.2 rather. It's all about if-then statements and conditionals, if you will. Conditional statements. Okay. So we'll do things like this. If P then Q. In other words, P implies Q like this. Okay. So there's that. So it is false when P is true and Q is false. Otherwise, it is true. Okay. Now think about that for a minute. So this is false when P is true, but Q is false. Well, why is that? Well, if you had a truth table, if this is true, then this is true. Well, that's true. If this is false, then this is false. Well, obviously that's true. If this is false, well, if this didn't happen, then we don't. In other words, like the police can't find your car if it's not stolen. Are you with me? So like this was like the thing, like your car is stolen. Well, that'd be just weird. So the idea that this is not stolen and then it's found, well, that doesn't really make any sense. You with me? So this one doesn't really make any sense at all. And then of course this one, my car is stolen. Uh-oh. And we didn't find it. Ooh, this is false. False. This isn't technically false. This is just weird. And these ones are both true. Okay. And so, I mean, this one's technically not false, but it's just weird. Okay. It's technically not false. Okay. And so that's pretty true. That's pretty true there. Otherwise it is true, you know, but it is. It's just weird, in other words. Okay. So when we do these guys, you know, just think about it here. So showing that P and Q, or P or Q, then R is equivalent to P then R and Q then R. Right? And again, it's an and situation. Okay. So can you show that that's true? Yeah, of course, I guess. He's good. And we'll go ahead and run through this. And once I think we do one of them, and then I'm not sure we'll do all the rest of them, but we'll see here. Of course, there's 8 outcomes. Guy gets tired of writing them all, but guy will continue to do it because that's my job. That's my job. Nice. Yeah, there they are, all 3 of them there. Now, notice that we need P or Q. So that'd be P or Q. And so what would you get? You would get true, 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 false, false, right? So one or the other one has to be true. Nice. So if you take these guys and you say this had to happen and then that, right? So true, then true, that's true. This is PV implies R. Okay? P or Q implies R. So again, the idea is if these are true here, the only time it's false is when this is true and that's false. So false, true, false, true. 1, 2, 3, 4, 5. This one's false, true, true. Okay. Now this one says P then R. All right, let's do P then R first. P then R is true, false, true, false, true, 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 true. Let's do Q implies R. True, false, true, true, false, true, true. And so I want to know the intersection of these guys where they are both true. So true, false, true, false, true, false, true, true. And if you look at this column right here, friends, which is this thing right here, you look at this column right here, you see we have agreement. What does that mean? It means that they are logically equivalent statements. So we're going to do some more logical equivalencies here. So if you say the negation of if P then Q is logically equivalent to P and not Q. Okay? Right? Could you show that's true? Yeah, sure you could. You totally could. So, ouch. A couple ways to do that, I guess. It'd be easier just to do the truth table myself. Once I do the truth tables, to me, just everything goes so much faster. And it's just a matter of just matching things up. So not Q. So I need P and not Q. P and not Q is false, true, false, false. Okay, so then not P then Q. Okay, so not P then Q. Well, I don't have P then Q, but it's not that hard to figure out. The only one that's false is this guy, right? That's the only one that's false. So the negation would be false, true, false, false. And because this is the same as this, they are logically equivalent. Boom. What? Done. Okay. So when you do if-then statements, so we talked about, so you can do, we're going to learn three other things, of course. You've heard them before. It's nothing big deal. The converse, the inverse, and the contrapositive. Okay? So just be in mind of these ones, okay? So we are going to say our proposition is always going to be of the form proposition if P then Q. Okay? So the converse of that, so the converse is if Q then P. Okay? The inverse is not P then not Q. And the contrapositive is not Q then not P. Okay? And, you know, it is what it is. Okay? Frequently, a lot of us, or you've heard a lot of times people say, well, conversely, but they actually use inversely is what they end up doing. Okay? So there you go. Conditional statement. So this proposition or the conditional. Oopsie daisy. So it says the conditional and the converse, conditional and converse are not logically equivalent. And what do I mean by that? Well, if you made a truth table for this and this, they would not match up. Okay. The same thing is true for the inverse. Okay. The inverse and the converse, of course, are the converse and the inverse are logically equivalent. Okay. What about the contrapositive? I don't know. Let's find out. So remember, if you just do two events, P and Q, okay. So P and Q, so P and, oh, sorry, probably P then Q. Oh. Right? Because the only one that's wrong is that guy. Okay. What about not P and not Q, not P? Okay? Not Q, not P. So this, well, that's true. This is false. This is true. This is true. So they are logically equivalent to one another. Okay? So pretty easy to do, pretty straightforward. I don't like the way your book does it. Your book always does it. See, to me, when I learned it, and I don't know, it makes the most sense about this, is the inverse, or the converse, just swaps them. The inverse negates them, and the contrapositive does both. Your book chooses to do this one right after the initial conditional. The reason for that is because they are logically equivalent. Okay, and then the other two are logically equivalent. Okay, I understand why they do it, but it confuses people, I think, so I don't like to teach it in that order. Okay, so P only if Q. If not Q, then not P. Is another way of saying if P, then Q. Okay. So they're just, and why is that? Because originally, what is this right here? That's the contrapositive. What is this? That's your initial conditional probability statement. Okay. There's another thing called biconditional. And you'd write it this way. It is exactly what you think it is. It is exactly what you think it is. So it has to be P implies Q and Q implies P. Which means, if you think about it, here's P and Q. I don't know why I did those backwards this time, but whatever. Everybody knows that this is the only one that is false going this way. Yes? And this is the only one that's false going that way, right? So if you think about it, both of these are going to be wrong this time. So if you do the bidirectional one, this one's true regardless of which way you go. This one is true regardless, and these two are both false regardless of which way you go. I can't think of a good example of a biconditional one right off the top of my head. Do some thinking about it. Maybe I could pull it off. But yeah, we'll see, I guess. Okay. So you want some order of operations. Some other things to come up in this chapter. The order of operations. PEMDAS. Please excuse my dear Aunt Sally. Ooh, we're not multiplying though. So when it comes to logical operators, first thing you always do is the negations. Okay? Then you're going to do these and these secondly. And of course, parentheses, I think, should be right up here, parentheses. They make note that if there are parentheses, you can blah, 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 of course. But obviously, if there's parentheses, then, if, for instance, this guy here, you need P and Q with a negative. We got to do these guys first, obviously, before you do this. Okay? Just be aware of that. And then, these guys, these are the third things that you do, would be the implies, whether they are biconditional or just the one conditional direction. Okay. Not a huge deal. We'll talk more about that as we go along and get some examples. I think it makes more sense when you do that. So this is the thing that probably is the hardest thing for me when I was a kid, learning this stuff. Okay. R is a sufficient condition for S. Okay. Means if R, then S. Or if you prefer, R implies S. Okay? If it is necessary, R is necessary. Now, I don't know why this was so hard for me, but I remember back in the day just scratching my head about this for the longest time because I could not grasp the difference between the two of them for class purposes. Means if not R, then not S, which of course means not R, not S. Oops. Okay. So, so this person was born on U.S. soil is a sufficient condition for her to be a U.S. citizen. All right, cool. Let's say you have to have your ID to buy booze. That's a necessary condition. No ID, no booze. I guess if you have a full beard of white hair and you're an old man that's bald, maybe that's a different story. But otherwise, you know, we card everyone. Good Lord, she's 95. I don't care. I don't see a card. You don't get any booze, friend. Okay. That's a necessary condition. Don't know why that was such a big deal for me. Back in the day, that was a very hard concept for me. In terms of actual applied stuff, it's not. But when you come into the classroom, sometimes you're just like, wait, something's weird here. I don't know what I'm doing wrong. Okay, so here are some truth tables. We're going to run through a few of them here and see what you think. We need to do a truth table for not P or Q implies R, like so. Okay. Now, again, what do we do first? Okay, well, this gets done first, then this, right? Because they don't need parentheses in this case because we know the order of operations for them. So let's go ahead and run these guys out again. Good grief. Here we go. So, oops, that's too many truths. Stupid. I'm going to do some falses. Now we need a little bit of not P action. Okay, so I need to do not P or Q. Let's get that done. So not P or Q. Okay, again, not very hard. Let's look at not P or Q. So I'm good here. If one of them is true, we're good. Yes, false, false, true, 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 true. Sweet. Now, again, we're looking to go from a T to a false to an R. From a T to a false is going to give me a false. Okay. So let's do this. So not P or Q, then R. Let's do this. We're looking at this column here and this column here. All right, we look at this guy first. So true, then true is true. True, then false, by definition, is false. False, then true is true. False, then false is also true. True, false, true, false. Done. It's that easy. Okay. Now again, truth tables, we can use them to show logical equivalency, and we'll see where we go from some of those. Let's find, for instance, this guy right here. Show that all the following are logically equivalent. All right, sounds good. It's P, Q, and R again, so I'm going to just copy this first part of the table here, if you don't mind. I don't care if you do mind, I'm copying it anyways. I'm tired of writing this stupid thing out. Copy, paste, done, sweet. Here's P, Q, and R. Sweet. So we want to show the following. We want to do P, then Q, or R. P, then Q, or R. Okay, we want to do P and not Q, then R. And we want to do P and not R, Q. Sweet. All right, let's try it, shall we? Okay, so looks like I need a not Q and a not R column, so I'm going to go ahead and do those real quick. Not Q. Oh, didn't need that, did I? Not Q is false, false, true, true, false, false, true, true, false, true, false, true, false, true, false, true. Okay. Then, there's anything else I need? I think that's all I needed. So then, remember, what are the order of operations? Okay, order of operations, this gets done first, right? Right? course I'm right. No, it's not, of course. Q or R. True, 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 false, true, 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 false. Okay, so that's this bit right here. You with me? Right? So then I want to do P, then this guy. So true, then true. So P, then Q, and or R rather. So T, then T is T, T, T. True, then false is false. True, 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 true. Sweet. All right, let's do this guy here. Remember, it's the and that happens first. So P and not Q. So P and not Q is false, false, true, true, false, 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 false. And then I want to do that implies R. Okay, so let's take these guys here. So false to true, by definition, if you're going that way, it's okay. Okay, so from false to true is true. True to false, oops, what am I doing here? False to false is true. True to true is true. True to false is false. False to true is true. False to false is true. False to true is true. False to true is true. Now, if you look at this column right here is the same as this column right here. That means they're logically equivalent. That's cool. So I've showed the first two are right. Now let's do this guy here. Let's go P and not R. So P and not R. False. True. False. True. False. 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 Okay. And then we're going to go from this guy to Q. So false to true is true. True to true is true. False to false is true. True to false is false. False to... where am I at? I lost my train of thought. To Q. We're going false to true is true. True, true, true. These ones are all true. And lo and behold, that is also the same. What does that mean? That means that they're all three logically equivalent. Okay? So then we're going to use logical equivalencies in part A to rewrite the following sentences in two different ways. If n is prime, then n is odd, or n is 2. If n is prime, then n is odd, or n is 2. Okay, so I'm going to call this P. I'm going to call this Q, and I'm going to call this R. All right? So what we have here is if n is prime, oh, I'm sorry, okay, so the way it's phrased right now is this right here. You with me? Okay, so let's do it this way here. Okay, if n is prime and n is not, and n is not odd, then n is 2. Okay, if n is prime and n is not 2, then n is odd. Bam! Okay, so that's kind of the purpose of that. You can rephrase them in different ways. Maybe ways that make a little more sense, things of that nature. It's pretty easy to do right there. Okay. So let's look at this guy here. Number 16, if you paid full price, you didn't buy it at Crown Books. if you paid full price, then you didn't buy it at Crown Books. That's cool. So then that's if you didn't buy at Crown Books or you paid full price. Okay. Make sense? All right, so we look at these two statements. Are they logically equivalent? Okay. So if you paid full price, then you didn't buy it at Crown Books. All right, cool. So when I say if then, what I'm saying is it's if, okay, so this implies that that happened. Oh, okay, nice. That's great. But in this situation here, you didn't buy it at Crown Books or you paid full price. They're not logically equivalent statements. They very say some similar things, but they're not. So let's go see if we can set this up here, okay? So let's do P, Q, okay? And let's set this baby up. Let's see what happens here, okay? Where P is price. And this one here, we'll go with didn't buy at Crown Books. One could argue that this is... One could argue that you could have made Q, you bought at Crown Books, and then you could have put in a term, a thing for not Q and gone that route too. One could argue either way. And one could be okay either way. It would work both ways. Okay, so let's do this. P, then Q. What does that look like to you? Well, that's true. That's false. True, true. Okay. The other one has an or right here, so that's P or Q, yes? Okay. Well, actually, it's Q or P. Okay, well, true, 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 false. So this one and this one are different. What does that say? It says they're not logically equivalent statements. Okay. P is a square, then P is a rectangle. If P is a square, then P is a rectangle. Okay, that's cool. So that's my conditional. Okay, then let's do first of all. So the converse of that just flip-flops them. If P is a rectangle, if Q is a, if P is a rectangle, then P is a square, which of course is wrong. Okay, that's the converse. The inverse is the negation. So notice that I did if Q then P. Right, so P then Q is conditional. Q then P is the converse. The inverse is if P is not a rectangle, is not a square. Then P is not a rectangle. Okay. Is that true story there? Mm-hmm. That's not necessarily true because P could have been a rectangle initially, right? Okay, but it could have been a circle, right? And that would have been the case, but we don't know. And this is the things I always hate. I can write these out. People sometimes like, this one's not bad. It's fairly cut and dry. Some of them are kind of weird, like, you know, are you depressed? Well, I don't know if I'm depressed or not when it rains or things like that. It's kind of weird. So if P is not a rectangle, then P is not a square. And that's the contrapositive. And it is logically equivalent to the first one because you cannot be a square if you're not a rectangle first. Okay, it's kind of like I've always said for years, you know, like if you'd seen an old man walking down the street and you knew he was a grandpa, all right, well then you know he's a dad. Okay, I mean, biologically, he's a grandpa. He had, like, his son or daughter had kids. He's a grandpa, not because of adoption or something like that. And I have to say that because otherwise, well, what if he adopted, or is there stepkids? Okay, I'm talking about his own personal kids, like in that true sense of the word grandpa, not like you have adopted stepchildren, which is great, and that's fabulous. You're still a grandpa, but I'm talking about in the strictest sense of that word. Do you know he's a dad? You kind of have to be a dad to be a grandpa in that way. Again, we're not talking about the fact that you could have stepkids and you know, you could have adopted a kid and what have you. But those things, just be aware of that. Kind of hard, but in either case, if then if you go, well, wait, stepkids, adopted kids, they're your kids, therefore you're their father. Well, then you're still a grandpa, and you know what I'm saying. But if you see a person who's a father, it doesn't mean he's a grandpa. Okay, so. But if you can tell me that person is not a father, then I know he's not a grandpa as well. Okay, so you know, it's a flip-flop of those things. Okay, let's see here. What else do we got? Ooh, a sufficient condition. Let's do a couple of sufficient conditions just for a good time, shall we? A sufficient condition for John's team to win the championship is that it win the rest of its games. Okay, so. No, a sufficient condition for S is R, means R is sufficient for S, means, and that is a necessary condition for S is R, means that R is a necessary condition. Rewrite them in if-then format. So, the idea is this, okay? So, what had to happen first? Well, if John's team wins the rest of its games, then it wins the championship. Yep. Again, that is a sufficient condition for it then. Okay. And then a necessary condition. So we need to write them as, we need to rewrite them in the if-then format right there. Okay, so that one right there is 44. Hey, let's do another, shall we? How about 46 here? If X is boiling, if the compound X is boiling, the temperature must be at least 150 degrees C. Assuming this statement is true, which of these also must be true? Okay, so check this out. So the temperature must be at least, so if it's boiling, if it is boiling, then temp must be, okay, clearly it's not water. Okay, cool. So if the temperature is at least 150 degrees C, then it's boiling. So so that's what they stated right here, okay? If it is boiling, the temperature, okay, so that's what they stated to us. Okay. All right, so then let's turn this around. If the temperature is 150, then it is boiling. Okay. Now, anybody have a problem with that at all? Okay, if you think about that. Well, what happens at 100 degrees Celsius with water? Okay, when you get to 100 degrees Celsius, what has to happen? You then have to input a ton more energy before she boils. Okay, so it doesn't necessarily mean that you've hit it's boiling yet, because, for instance, there would be. So I don't like the way the book does it, but I looked at their answer just to see what they put back there. Because me personally, I'm looking at this from a strictly science point of view. As you know, 1 liter of water is 1 kilogram of water. For every kilogram of water, you need to input 2,260 kilojoules in order to get that to boil. After it's reached the boiling temperature, which is 100 degrees Celsius. So it may or may not be there. But the book also mentions, listen, if it's boiling, it must be at least 150 degrees. Well, that's true from the standpoint, check this out. If water is boiling, it must be at least 75 degrees Celsius. You're not wrong. Okay, you're not wrong. It's greater than 75 degrees Celsius, because you know it has to be 100 degrees Celsius to boil. I don't like the book's way of doing that, but it's not inaccurate. It's just weird. If the temperature of compound X is less than 150, then the compound is not boiling. If the temp is less than 150, which is the negation of this, then it is not boiling. Okay, well, think about that. Okay, well, this is the negation of this. That's the contrapositive. The contrapositive and the conditional are always logically equivalent. So, in fact, that has to be true. Okay, let's do part. Is there another one here? Yeah, part C. Here we go. Compound X will boil only if its temperature is at least 150 degrees C. Pause for a second there. All right, I'm back. Sorry, I got interrupted there again. Working at home is sometimes a challenge. Have you noticed that? I don't know if you've noticed it. I've noticed it. Remember where I left off. I'm going to start off with this truth table. This is number 48. Okay, so we're going to use logical equivalencies. Use the logical equivalencies that P then Q is equivalent to not P or Q. And the biconditional is equivalent to not P or Q, and where did they, oh, for God's sakes, not Q and or P, or P. All right, so use the logical equivalence to rewrite each statement of the forms without using the conditionals. Okay, and use the logical equivalence that P or Q is logically equivalent to the negation of not P and not Q. Okay, to rewrite each of the following statements. So we want them to be only ands and negations. Okay, so what I want to write is we want to rewrite this guy P. No, I don't want to do the one for you. I want to do my own P or Q. P or not Q, sorry. R or Q. Okay, there we go. Nice. Applies. Yes, there we go. Cool. Love it. Love it. Excellent. Okay. Nice, 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 nice. Okay, so there we have that. So we're going to use these logical equivalencies and that logic to rewrite the given statement without using those. Cool. And use a logical equivalence that is that to write each of the statements using that and that. All right, cool. Cool. All right, so P then Q is equivalent to not Q, no. All right, so I'll get pause for a sec here while I look at this. So we want to look at these guys here. I'm going to stare at them a little bit more. I was going to try to do out the whole truth table. I'm not sure I want to do that. I think I might want to just go do a little algebra here and do some messing around. Let me pause for a sec while I look at that. Okay, so if you write like this, that is our P, this is our Q, and it's logically equivalent to not P or not or Q, which is this guy. Interesting. So let's think about what that would be. Okay, what is it? Well, the negation of this whole thing then is what? Well, if you look back on page, get that back for you, back on well, let's just do this. Let's just actually do a truth table for that. So let's do that. So if you did P Q, so that's, I need a not Q, sorry, I need a not Q, so false, true, and so I need a P or not true. So P or not Q. That'd be true, true, false, true, and then I need the negation of that. So that'd be false, false, true, false. Okay. All right. So if you look at that, what is that? What is that? And that's back on page, oh, for God's sakes. Table fiddle. I was going to just point it out to you so you could see it back there. Page. Aha. Yeah, so not P and Q is, not P or Q rather, is not P or Q is not P and not Q. So this is equivalent to not P and not Q. Okay? So this would be not P and not Q. Okay, it's from back on that page 35. Okay. Okay, cool. Now, now they wanted us to get rid of everything except for the ands and the negatives. That was their thought for us. Yep, they wanted us to rewrite it using only ands and negations. Okay, so what is, so when we look at this business here, what would logically be equivalent to that? Okay, so this, so I need to get rid of this and this. I need to rewrite them. Okay, and it said here at this juncture, we need to take this guy right here, right? And we need to change this into an and statement somehow. Well, if you recall, they told us to use this guy is logically equivalent to not P and not Q. So in our case, it's going to be not R and not Q. Okay? Okay, well then I'm going to use the same one again to pull that off, right? So I want the negation of this thing. Something like that, huh? Okay. And then did they give us anything else? I think that's all they gave us to work with. I think that's all they gave us to work with that we need to fool with right now. Okay. I got down to what they wanted, which is all ands and negations. Okay. So yeah, I find them somewhat fun. Sometimes I find them annoying because you have to kind of keep going back and look at your equivalence relations. And what can I do for substitutions? And it's not as obvious as like in trig. Like in trig, you're like walking along, you're like, oh my gosh, I see sine squared plus cosine squared equals 1, right? And you just see, like, oh, I can put a 1 in there, awesome, or 1 minus sine squared or whatever. But why? Because we beat those into your heads over the years. This is not as obvious. After you've done this sometime, and even I'm not good enough at it because I don't do it often. If I teach this class once a year, and every time I teach it, well, obviously I get better at, smoother at it. But every time I teach it, I find myself going, oh, I memorized one more thing to the point where, yeah, that's my thing. Now, statistics, for instance, is my thing. Calculus is my jam. Diffie Q is my thing. Those guys, I don't need to do a lot of thinking anymore. Well, mostly because I teach them multiple times a year. I've taught them for a long time now. But people in the class are like, how did you know that? You just figure it out over time. So the same thing's true here. There's going to be some of these you're going to scratch your head and stumble on. Sometimes you'll get to a situation where, I mean, you might have plus 14 cosine x minus 2 secant or something. And like the book cleans it up and it writes it really small. And you're like, how did they do that? Oh, I didn't see. I could have substituted here or something, right? You know, things like that. A guy could just, you overlook them because you're not there. This is a situation where in this case here, you know, you could probably take it down further. Problem is you take this, the negation of this puts you back to an or, so I don't want to do that. So my point is when you do these, don't get too frustrated or hung up on it. Don't worry too much about it. If you make heads or tails out of most of it, and then once in a while you run into one that really makes you like scratch your head, join the club, pal. Join the club. Glad to have you.